SIW slot antenna. So we had designed this SIW waveguide. This is an SIW waveguide. Here we have a substrate, and let me remove this one. And here we have a ground plane. So yesterday we designed an SIW, and for that initially we designed a ground plane, that is the bottom layer of our PCB. Then we designed a substrate over this PCB. After that we designed a top layer. This is a normal PCB, and in this top we have a cutter slot, and in addition to that we also designed these cylindrical rows. So this by this we have implemented a sidewall of the rectangular waveguide. These are the two sidewalls, and this is the top sidewall. So what happens in waveguide based slot antennas? If we go through the theory of this kind of slot antenna, so this is a typical waveguide based slot array antenna. So here we have a rectangular waveguide, and that waveguide is extending in Z direction. And in our design, we have put our waveguide in along the Y-axis direction. Then on this waveguide, these are the sidewalls. This is a normal rectangular waveguide. This is not an SIW, but the working principle remains the same for both the antennas. So in this one, we have several slots that are cut along this, and these slots are called longitudinal slots. And uh, there is a theoretical derivation for these slots, and these are the current distribution along these slots. So in this current distribution, we can find that this the offset value that we added there, that has a deep impact on the current distribution. Okay, so this x is given the sinusoidal due to sinusoidal variation, the sine function is there, and this x is the displacement from the axis. For example, yesterday we designed this, and if we see this this slot, let us go to top view, and now in our design parameters we have taken a design parameter x offset. So if we increase this offset, the slot will move up from that side. So from the y-axis is the center axis of this SIW. So when we are shifting this offset, then we are changing this x. So that x will be put here, and a is the width of this waveguide. So according to this function, our current distribution will get disturbed. Both jx and jy component will be disturbed. So we can use this x offset to match our impedance. Similarly, we can have a transverse slot that is normal to the direction of propagation of waves inside the waveguide, and we can also tilt that slot, and with tilting we will be getting a slant polarization. Now next, what is in waveguide we can have multiple slots. We can put one slot here, one slot here. So if you see, we are placing these slots alternatively. For example, here if we see, this slot is in the right side of the main axis, and let me create one copy. So here I will be deleting this operation. So this is a slot. Now if I want this length of the waveguide to increase and I want multiple slot elements, what I can do, I can set it to uh, 25 is 3. Okay, let me make it 41 mm, and now I make it mirror copy of this one like this. So you can see both uh, the elements are mirror. Then we make give it a displacement, and how we are calculating the displacement that I will explain, and why we are placing them one in the right side and one in the left side. That is also I am going to explain now. So let us go back to this. So here whenever we are designing the waveguide slot antennas, we are placing them along the uh, uh, alternate places. And yesterday also I have given told you that the first slot that we will be placing, it should be from the at the center of this slot should be from lambda g by 4. Lambda g is the guide wavelength inside this waveguide. So that should be lambda g by 4. So why is that? Because if we see here, this is the end of your waveguide, which is short circuited. Okay, so anything in parallel with the short circuit will give a zero impedance. But as we are working in microwaves and in traveling waveguide, so what happens in a transmission line, when we are traveling along the transmission line, the impedance gets changes according to the formula, transmission line formula. So when we put this d equal to lambda by 4, equal to quarter wave. So for a quarter wave traveling, पेन बंद कर दीजिए सर, पेन बंद कर दीजिए सर. Okay, so for when we travel lambda by 4 distance along the transmission line from a short circuit end, then we reach to a point where we get an open circuit. So the short circuit will act as an open circuit at this point if this distance d is lambda by 4. So that is why we are keeping that the distance between the slot, center of the slot, and this uh, and the terminal should be lambda by 4, lambda g by 4, right? Guide wavelength by 4. Okay, so that this will have only the at the impedance that we look at this, that will have the real values. Now uh, from this point, for example, this is your last slot, and after that we have a distance of lambda by 2, so that when we are using the formula for transmission line, and we are propagating in the transmission line for one sorry, one half cycle, then the impedance remains the same, right? So that is why we are using this kind of antennas. Now, this arrangement where we are placing the slot lambda by 4 distance from the end, and the open end from where we are feeding. This should have a distance of lambda g by 2 from the center of the slot. Okay. Now, why we are placing this in an alternate arrangement? For that, let us try to simulate this one. Okay, I think there was some execution error. Okay, so I will show you the existing results. I have this one. Okay, maybe it's X. So said it was 0.5. Okay, now our results are present at this parameter values. So first, let us analyze this field distribution. So this is a magnitude field distribution. Okay, sorry. So in this field distribution, if we go here and go to isometric view first, now right click on this and click on the modify plot. So right now we were observing only the magnitude. Now what happens if we observe the electric field? And let us go to the right side view. So in electric field distribution, what we can observe, from this point to this point, our electric field is downwards, and from this point to this point, it is upwards. So it is having a half sinusoidal variation. And let me check if I can go and take it to 15 gigahertz. At 15 gigahertz, let us observe this one first. So here you can see that there are multiple half-wave cycles, and when we go to this right side view and we change this to vector electric field, so now you can see that for every half wave length, we are our direction of electric field is changing. So that is the reason why we prefer the slots in the first slot is in left direction, the slot next slot is in right direction. So this is the alternative arrangement, the reason for alternative arrangements of the slot. Okay. Now let us go back to 9-10 gigahertz. And so if we click on animate, you can see that our electric field is moving across this plot. Okay, so that will resolve the error. So if in this field the electric field is moving up like this, and when we will be seeing the electric field at this point, we have to place our slot here so that it will have the same polarization. So that is why we are using alternative arrangements. Then right click and modify to magnetic field distribution. So from magnetic field distribution, we can see this length is matching the approximate uh, guide wavelength, the half of guide wavelength, and it is placed from here to here. So in order to design this, what we can do, we can first we can remove the slot. So I added a variable yesterday. So first I make it 1. Now there is no slot inside, and now we simulate. So this guide wavelength you can calculate from the formula and determine, or you can directly use the simulator and find the guide wavelength. Yesterday I have showed this one. So you can calculate the lambda. This will give you the guide wavelength inside this medium. So we are trying to design antenna around 10 gigahertz. So the guide wavelength at 10 gigahertz is 31 millimeters. So this is giving in meters. So it is 31 millimeters in distance. And at 10 gigahertz, when we draw this line, uh, then uh, when we see the electric field distribution, we can see that we have a complete half cycle, then we have a quarter wave cycle. Okay. Now, when we see the jet field, so we see that there are several spikes here. So right click here and add markers. You can observe that we have this first peak is at 8.38 gigahertz, second peak is 10.15 gigahertz, the third peak is 12.98 gigahertz. So let us see the electric field distribution or at all these points. So the first peak was 8.38. If we have this 8.38 gigahertz, here you will see that this is around the cutoff frequency of the waveguide. So at this point, we have a very large guide wavelength. Okay, then we have the second peak, and so it is a quarter guide wavelength. Now we have a second peak that is around 10.15. Again, go here 10.15 gigahertz. So now we will be having three quarter waves. First, only single quarter wave, then three quarters wave, and at around 13 gigahertz we have 5 lambda g by 4. So here we can see this is lambda g by 2, lambda g by 2, and lambda g by 4. So in this, what we can do, we can design and two slots, one slot here, one slot here, and that both the slots will radiate at the same frequency. So now the question comes, how do we calculate the length of this slot? So the length of the slot, we can calculate it from the free wavelength, free space wavelength. So as we know, the guide wavelength is always greater than the free wave space wavelength. So we can calculate the free space wavelength and use that here. Sorry, not the free space, but the wavelength inside the waveguide. Okay, so that will be free space wavelength divided by square root of epsilon r, and the guide wavelength is slightly larger than that. So we calculate the length and put that value here. So and after some tweaking, we can get the results. So for this, uh, we are getting the results. Let me again put this slot here. Now the slot length is around 13 millimeter. So the free space wavelength was around 30 meter. So the slot length is lambda by 2. So it was 15 millimeter, and for due to the concentration of dielectric material and other limitations, we are getting it 13 around 13 gigahertz. It is radiating at 10 gigahertz. So let us see the field at 10 gigahertz as well. So at 10 gigahertz, we can see this electric field is there, and these are the Z parameters. These are the S parameters of this antenna. S11, the return loss is there, and the antenna is radiating around this one. And if we see the impedance, the impedance is slightly varying in this frequency. So again, we need to calculate, move the wave port, apply some de-embedding so that we can easily identify at which frequency we are having that. So the jet parameters are highly affected by the position of your port. Now, uh, and finally, we can calculate this one. Now, we can also add some field network. We have not added a radiation sphere. So in order to check the far field, we have to add radiation sphere, and we will be selecting this infinite sphere. 10 degree, 10 degree, and click OK. Now, if we try and create the far field results, go to 3D polar floats, and then float the total gain. Sorry, change the sweep, apply. So right now it is plotting the field at 8 gigahertz. We want to check for the 10.15 gigahertz. Now apply. So here what we are able to see, we are having a gain of 6.72 gigahertz. Let us check the realized gain. Realized gain is also 6.6 gigahertz. Okay. And if you remember from our last simulation of the microstrip patch antenna, the gain of that antenna was around 2 to 3 dB. Here we are getting a increased gain of 6 gigahertz. So that is why we prefer waveguide based antennas. So what happens in waveguide based antennas, if go and orient in the left axis, now you can see uh, that most of our field is unidirectional, and the backside has reduced the side lobe. So that means the power that was being transmitted in both direction, now it is a unidirectional antenna. So that is why the gain is increased. And so this is how you can design antennas, SIWS slot antennas. Now there in SIW there are several other factors. For example, if this slot antenna and this number of slots. So what happens when we are controlling the offset? If I change this offset, change the offset to 1, and if we simulate it again, so you can see there is a very big difference just by moving the offset by 0.5 mm. We have got a very huge difference, around 10 dB shift in the S11. And if we see the Z parameters and go to real impedance, so here we can see uh, at this point the impedance was this one, but now it has shifted by a huge amount. Now, why we are seeing these two peaks here, and if you observe, when X was zero point 0.5, the peaks in the Z impedance, the real part of the Z, were from like this, from at 9.6 gigahertz and 10.5 gigahertz, whereas the peaks for x offset equal to 1, the, the difference between these two is increased. Now it is 9.5 gigahertz. The lower resonant frequency has shifted at the lower side, and the higher frequency is shifted at higher side. So if we observe these fields here, now uh, here we will be looking at the 9.5 gigahertz and 10.9 gigahertz. What do we observe? 9.5 gigahertz. At 9.5 gigahertz, you can observe that most of the electric field is making a half cycle here, and from this slot it is radiating, right? Again, let us observe at 10.9 gigahertz, 10.9. So at 10.9 gigahertz, we observe that from this point to this point, we are observing a quarter wave variation, and at 9.5 gigahertz, we were observing a quarter wave variation between the sidewall and the slot, and 10.5 the variation 10.9. So at 10.9 gigahertz, we have a quarter wave variation between the sidewall and the slot. So this kind of basically we are getting two modes here, but those modes are not effectively reduced because if we see the amplitude of this slot is 180 and 192 for the first case when x offset was zero point 0.5. In the second case, we are observing the point is 300 and 100. Okay, so by this we when we shift to this x offset, so either one of the value will reduce and another value will increase. So we will not be able to simultaneously excite both these resonances. So that is why we make a compromise and we observe the effect where this parameter if we see, go to y-axis and set limit to 500 and click OK. So now if you see here, uh, this is your the red part is your real part of the impedance, and this green zone is your imaginary part of the impedance. And at what point we are observing the dip? We are observing the dip around this point where the impedance is 30 and the imaginary part around is around 0. Okay, so at this point we are observing the dip here, so that is why there is a huge shift in the frequency also. You go here, select the S parameter, and for both values of this x offset, we are observing this variation. So this variation is because one of the uh, peak is varying. Now, if I reset this x to 0.5, this x offset is 0.5 now. So this red curve was there for this one. So here we see the observation point. We are getting a good matching at 10.1 gigahertz. And when we see the Z parameters of this one and right click here, double click on the y-axis, then on the y-axis we give this axis range to 500 and click OK. Okay, go to X scaling and set this to minus 200 to 500 and click OK. So now you can see that these two peaks are there. So these two resonance points were there, and if we place a marker and check the value at 10.1 gigahertz, so at this point, what we observe, uh, the first resonance that was between the left side wall and the slot, and this was between the right side wall and the slot. So both these have around 250 ohm of impedance, and at this point, the impedance is decreasing, and the second resonance has it started taking place, and it started here. So now the impedance is 70 ohm here, and real imaginary part is around zero. If it is zero, then at this point 69 to 70. So at this point we are getting a good matching of the impedance, and when we vary this x, then we will be observing a shift in this matching point. That is why the difference in this frequency is there. Okay, so basically for all the slots we will be getting two resonances, but we have to optimize them to match our desired frequency range. So this is one method, and what will happen if we have multiple slots? So if we have two slots, then the and both the slots are at this exact dimension. Let me check if we can do this. Okay, so let us subtract, and I think I made some mistake here. X offset 0.5, and it length. Let us try to simulate it now. So there is a direct formula that says that if we have n number of slots, identical slots that are placed alternatively on the opposite sides of the waveguide axis, and all the ports have same offset, then the impedance of will be around uh, 1 by n square. So if original impedance is around 500 ohm and we have put two slots, then the resultant impedance we will be getting around 125 ohm. Okay. So by that using that we can also use this. We can increase the number of slots. Of course, increasing the number of slots will increase your size of the antenna. Then also, it will increase your gain also. So now we have multiple slots. So if you see, we are getting an peak here. We are getting a good matching at 9.55 gigahertz. So let us see what is happening in the Z parameters. So in Z parameters, if we click here, go to Y scaling and set it to minus 200 to 500 and click OK. And we are interested in 9 gigahertz to 11 gigahertz. So again, go to X scaling and check it 9 to 11 gigahertz. Click OK. So now you can see that there is a peak around here. At this point, there is a peak, and that peak is 63 ohm, and imaginary part is 0. And the next one is around 150. So the amplitude has increased at this point. So our matching has decreased from 10.1 to this one. Okay. So there might be some parametric differences when we created a copy of this one. And of course, another limitation is if we see this plot the field at 9.5 gigahertz, and so at 9.5 gigahertz we see the first resonance between the left sidewall and the slot, and here we are having the same resonance but right waveguide and the slot. So the distance between these two is identical. So that is why we are getting this slot. And now if we zoom in, another area that we can further explore is you see this slot at this slot this variation is about the center of the slot. The peak electric field is about the center of the slot, whereas here we can see that this slot can be moved low to the lower side, and that will increase this field, and that will also help you increase your gain and matching. So here let us because the wave guide wavelength, if we measure here, the guide wavelength is around 31, and we have moved the slots. The movement of the slot is around 15. So 31, that means we make it 15.8 millimeter, and then we simulate this one. So this is the principle, and I was showing you a paper yesterday. That was my paper, and in that I have used these both the modes. Okay, so this is a work from my PhD thesis, and in which I have placed two slots, and this was the formula that we used. You can take a screenshot, or I will send this one. So from these sorted wire slots, we will be placing a slot, and the center of that slot is from lambda g by 4 distance from this point, and the next slot that we are presenting, this difference between these two slots, the center of these two slots should be lambda g by 2. So I designed this antenna at 28 gigahertz, and I changed the shape so that I can utilize both the slots, both the modes. So you see here, this is uh, a result where only one end slot was present. So at that point, we were having around 300 ohm peak, uh, and then we check the field distribution. Current distribution will also give good insights, and from the electric field distribution, we also observed the same effect that one of the slot was between this sidewall and the slot, and the other was inside the patch. So we created this one. So in this design, I use both the modes to increase the uh, I use both the modes to increase the bandwidth of the antenna. Uh, how do we define the bandwidth? Bandwidth is where a certain parameter is matching. So normally for an impedance, there are several kind of bandwidths in the antenna design. The number first one is the band impedance bandwidth. Impedance bandwidth means when where S11 is below 10 dB, that is called our impedance bandwidth, because at that point our impedance is matching. And another one is uh, uh, gain bandwidth. Gain bandwidth is basically from peak value to how much variation is there. Then we have half power beam widths and other things. Then we have excel ratio bandwidth. Excel ratio bandwidth is if we are designing a circularly polarized, then we can calculate the excel ratio at all the frequencies, and uh, at the in the range of frequencies where excel ratio is less than that 3 dB, then we have excel ratio bandwidth there. Okay, so this is a first method in which we add some slots in the white SIW. Okay, so basically, if you have a constraint on the design of you have hardware constraint, like you don't have sufficient RAM, and you want to simulate this kind of antenna. So what you can do, you can start with a simple rectangular waveguide, and no need to use the side walls as vias. You can place the side walls here. Then you can uh, apply your slot design here and check the variation. You can optimize the size of the slot and its dimension. Then once you have satisfied that this is the results, then what you can do, you can select the you can replace the side walls with the vias according to the size that we have, the formula that yesterday I have shown you. That formula was around, using this formula, your actual sidewall distance is A. So you design this D and S and to calculate the A effective. So you will be placing the vias at this point. So they will be slightly outside. So we will have a broader waveguide there than the original one. So, this is the first method in which we add the slots in the waveguide. Another method is we can create cavities. In cavities, we have waveguide back cavities, cavity back antennas for rectangular waveguide, and we can implement them in our SIW also. So, what is a cavity back antenna? For example, let me go to this our previous project. And from this project, I will be selecting the patch and direct fit patch antenna. So this one I am selecting and copying it into the SIW project. Now, what I am going to do, if you are not able to recall, I will display you. This is the reason. So let us make it invisible. Now fit all the elements. So we in this we have a ground plane. Then we have a substrate, and on that substrate we have a patch. Now in the ground we have made a hole so that we can feed the antenna. So this small here. Then we have a cylinder of dielectric material that you use for coaxial cable feeding. Then we have two cylinders. This one is the center conductor. This one is the outer conductor. Then, if you want to actually realize a coaxial cable, you can also place one more cylinder here that will be used for shielding. Or in real life, we have a coaxial cable that has multiple layers. So here we are only implementing three layers: the outer conductor, the dielectric between the conductors, and the center conductor. Okay. Now, what happens if I place this antenna inside a wave cavity, made up of walls. So we on the ground plane we have already have a wave, this conductor. Now if we place a conductor like this, we place side walls like this. So I will be giving it minus position minus W cavity by 2, minus W cavity by 2, and I am starting it from T. I am keeping cavity to 50 mm, and X size I am taking as T, Y size I am taking as T. Uh, we need to increase this, so W cavity, and Z size we are going to keep it X. So like this is the cavity that designed. So we place this one around here, W cavity and T. So basically, if we put our antenna inside a box, you might have seen that in order to increase the efficiency of routers, what we can do, we can place a bottle, metallic bottle, to make a shield, a reflector, and that will increase the size. So what happens if we place all our antenna, and let me, this has been placed to minus 25, and what is the size of this substrate? Substrate is minus 25, 25. Okay, so let me remove this and go back here. What I am trying to do, I am trying to create a rectangular box here that will enclose this antenna. Okay, so now uh, on this in this box, I'm going to apply certain boundary conditions, or what I can create. Select a face. I select this face and right click on this and go to edit and create a surface from this. Create an object from this face. Also, I will go select one by one. I will select all the faces. Go here, edit, and create another face object. Now select another face, click edit, go to surface and create an object here. Again select next face, edit, surface, create an object. Okay. So now we have four faces, and let us verify we are starting it from 0. And okay, now if I delete this, so what we have done, we are able to achieve here. We have created a hollow box, and this one is touching the boundary. So let me, yeah, in that box, so 10, 10, make it 45, 45, so, no, 25, okay, it was not 10, now we should be placing it to 5 only. So now if we see this one, we have a rectangular cavity like this. Or let us check the patch dimension, and we will. So patch is starting from minus 19 and 10. So I will be giving 5 millimeter padding around all the axes. So 24, 5, and I forgot to note down the dimension. The 38 and 28. So 10, 10. I will create this one. 38 to 48 and 28 to 38. Now we have created a box around our patch, and then we have from the sides of the box we have created faces. Now we can delete this box, and if we observe here, now our patch antenna is placed inside a box. So now let us give all these boxes a boundary condition. Right click here, assign boundaries, go to assign boundaries, and for conductors we can give perfect E condition conductor. So when we apply this, all these side walls become conductive. Okay. Now click analyze all and see the results. What is happening? Originally we had this patch antenna here, and the results were around that. So originally the patch antenna was radiating at 2.4 gigahertz, and it has a good band impedance matching, around 20 dB return loss is there. The impedance is around, the peak impedance is 125, and we could have matched it properly. And, let us say now right click here, insert a field in this one, so we can measure the gain. Okay, now go to far fields and go to 3D Polar Pro, and around 22.4 gigahertz we will be measuring this. At 2.4 gigahertz, what is the value of the gain, the realized gain in dB? You apply. So at this position, we have a gain of 2.8 dB. I think we have selected yes. So the gain is 2.8 dB, the maximum gain. Now, when we have enclosed this by this, and first check the S parameters. There is slight variation in the in so the frequency has shifted. So the reason of for that is earlier we had a very around 125 ohm was the value for the real impedance. Now it has shifted to 2.4 200 ohm. So once we start decreasing, so earlier we were obtaining around this point. Now we are obtaining a 50 ohm around this point. So it is all about impedance matching, where the impedance is being matched. So that is why there is a shift. If you had designed this antenna in such, if you had optimized the dimensions of this patch, so if we optimize the dimension of this patch in such a way that the peak is appearing at the 2.4 gigahertz only, and the port is around 50 ohm, then we will be having exact matching there also. Now, for demonstration purpose, I am not going in detail there. So right click here, insert a field here also. Click OK. Now I will be checking the field at 2.44 gigahertz. Go to realize gain, dB. Okay. So the gain, in this case, gain is reduced. I will I will check it why it is reduced. Let us say if the object that we created has only, yeah, now what will happen? It was a surprise because when we are enclosing with the uh, dielectric materials, okay, I think complete perfectly and the radiation works. It should have increased, but let's see what is happening. Okay, so let's check here. What is possible? Okay, so Afrin was asking about what is the significance of half cycle variations. So half cycle variations determine your modes in the waveguide. Uh, if we have a half cycle variation, if we see here, here check your magnetic field at different frequencies. We check this field distribution. I think the results are present at this combination also. Yes. So now at this point, what we can observe that in this waveguide, we have almost two half wave cycles around, and if we increase 10.2, so at 10.2 gigahertz, the half wave variations are two complete cycles. So it is T to 0 mode, okay, to 1 mode, because in x-axis also we are having one variation, one half wave variation. In y-axis we are having two half wave variation. So it is T to 1 mode, and if we increase to 15 gigahertz, so here we are at around 14 point, maybe. Here we are having T31 mode of the waveguide. Okay. Then I will answer the next question once we go through this one. Okay. So now when I decrease the size of the field, the gain is around 2.8 gigahertz, very slight variation. So basically, we wanted to cover this with this side walls and check the results. Okay. So now, if we select this one and if we go here, the box in the box, earlier I gave a padding of 5 mm. So that's WP by 2 minus padding. So now I am creating a padding, and this was LF maybe. Now let us give this padding as 10 mm LF minus padding. Okay. Now the which will be WB plus 2 times padding, and LP plus 2 times padding, and Z size ZP. So now we have made it a variable. Now 10 is extending beyond, and I want this padding to be 2 mm. So if you can observe this, let me remove this one and this one. So you can see this border here, and all the borders, if I increase the thickness to 1 mm, you will be able to observe. So these 4 boundaries we have created. So these boundaries are made up having a now the material to this is, so change the material, assign the material, and we will be giving it copper. Now it is a solid material. I am just increasing it because new definition is not ready already. Okay. So I'm just increasing the thickness so can you can see what is there. So this now we have enclosed this patch with this walls. Okay. Now and what is it? What we do in waveguide? We in SIW we will implement these side walls by the wires. So now if I try to simulate it, and this time I have kept this distance 2 mm only, and then we will be in varying this distance and observing the results. So there is an error that says part. Okay. So what we can do, we can just add all these. Okay, there is a zero error. So this is overlapping with the ground and the substrate, I think. Substrate, from substrate it is there. Okay, from in ground also. So what we can do from ground, we will be cutting these objects and creating a clone of that. Then from the substrate also, we are going to cut this part. So if you recall from our first lecture, I told you that there are some limitations there. And another thing is that we have created this. So now the error is at this point these two are touching. So that is why we are getting an error. So if we kept it to we remove this thickness, then there will not be any issue. So let us remove this thickness, and the clones, we will not need the clones also. But you can visualize here that we have placed the conductive boundaries at around this. So that are the side walls. So I will create this one. Again, I will remove this one, and we need to make sure that when we are going back to the sheets, we are converting them back to sheets. They remain with the boundary conditions. So, okay, so the boundary condition is still there. Now, if I increase this padding, this box is increasing. Okay. So let us start with this 2 mm. At this point, let us simulate this one. Okay, so if you search for cavity backed antennas, and this antennatheory.com, this is a very good resource for electromagnetic engineers, especially antenna engineers. So what happens? A cavity is a metallic, hollow metallic box which has all the surfaces closed. And in cavity back antennas, we place our antenna inside this cavity and make one of the side wall open. This is not there. So you can see this is a spiral antenna, and we have placed a cylindrical cavity here, and it is closed at the bottom side with a gap for the feeding. So like this, we can create our antennas, and this cavity we want to implement inside a planar circuit. On the PCB, we want to implement it. So what we can do, we can replace the sidewall by the vias using the same formula. And now if we see the S parameter has slightly improved. And if we see the gain is 2.7 from 2.5. Now if we further reduce this gap, then see what happens. We have to plot this different variations of S parameter with respect to padding. So there is a shift in the frequency, and why that shift is coming. So if we go to Z parameters and print the real part, the peaks are varying slightly. We make this realize gain, and now the peak is exact 2.4 gigahertz. 2.4. So not much effect, but I will give you one example tomorrow. I will do some workout around this one. Uh, Anyways, if you want this kind of a structure and like type SIW cavity back antenna, so in SIW cavity back antennas, we can have cavities made up of the sidewalls made up of wires and like this. So here there is a patch antenna and these are the sidewalls. This is a slot here, and we are adding this cavity. So basically what happens when we are adding the cavity, it reduces the backside lobes, back lobes. So when the back lobes are removed, then they might be focused inside the in the positive direction. So that all depends on the size of the cavity, the height of the cavity. For example, if you see here, this cavity has a very huge height. So that height is a factor there. Also, when we are using this SIW, then there is another impact, that is quality factor of the device increases. So when the quality factor is increasing, then your bandwidth will decrease. So there are certain advantage and disadvantage of using SIW here. Okay, and that is all for today. And now I see there are several questions. So from Afrin, I hope Afrin, your question is you are clear about the wave outflow cycle variations. Then okay, this is not, what is the TE mode by the electric field? graph. So that TE mode is basically when we plot a uh, electric electric field, then we observe the variations, how many half cycle variations are there. Then Abhishek is asking the Viva are hollow cylindrical structure in the design and SIW are metallic cylinder. Okay, so you might be confusing. Uh, in this design, just for the sake of visibility, we are displaying hollow cylinders. Okay, we have only cut the cylinders here, and if we want that, then through hole plating a technique is there. Through hole plating, in which what happens on this sides of these on this walls, only the metal will be coated. So that will remain hollow, but the sides, that wall has been realized by through hole plating, in which this now it has very thin layer of conductive material. These holes have very thin layer of conductive material, and in our simulation, what we are doing in simulations, you can see these are the complete cylinders. So it does not affect your results because whether you are using a filled cylinder, filled conductor, or you are using a hollow conductor, because the electric field inside this will be zero, because we cannot have electric field inside a conductor. All the field that is coming, that will be reflected from the side walls only. So when you are going for fabrication, they will have only that they will have only where uh, you will be able to see through the holes. So let me show you in my thesis also. I have some fabricated structures. I think this figure is uh, of better quality. So here, if you will observe, uh, these are hollow cylinders. Okay, so these are hollow, but inside the walls, the walls of these holes are metallic. Okay, SIW and via in terms of their structure. Okay, so for simulation, you can design a filled cylinders because there is no need to do extra work. If you want to implement this hollow via, then you can create two cylinders. For example, let us say I create a cylinder, and this the radius of this cylinder is 4 mm. Now I create a copy of this cylinders, and in this cylinder, I am giving a radius of 3.8 mm. Okay. Now, if I subtract this cylinder, so we have a thin wall, and when we rotate it, it is a hollow cylinder. Okay. So, in practically when we are fabricating, we have this kind of cylinder there, and the walls are coated with conductors. Okay. So, if you want, you can implement this. Otherwise, I don't think there is a need for creating this one extra step there. Then, how to integrate discrete component in HFSS. Okay, sir. So, we will cover this in next session. Afrin, can you explain how can we identify polarization from electric field graph? So, Afrin, the polarization. Right now, we have not implemented any what we say. Right now, we have not implemented any circular polarized antenna, so we can verify the electric field distribution. And this is a linear polarized antenna. So what you can do, you can go here and on the surface of this patch, uh, just remove this one. On the surface of this patch, right click, go to plot fields, go to electric field, and click vector electric field. Okay. So now you can observe the direction of electric fields and which field you should be focusing. You should be focusing which has the maximum magnitude. So this green field that has the maximum magnitude. Now you select this vector field, right click on this, go to animation and reduce the size so that you can have better visibility. Now what you can observe, the field is fading and there is a sudden shift. I think it got the speed is still taking. Okay, so what we can see, select this one and in the properties you can see the phase. Right now it is 0 degree and this field is facing upside. Okay, increase it to 10. Still it is facing the upside. Increase it to, okay, there is one thing I missed. First we need to check at 2.4 gigahertz. So right click, double right click here, go to modify plot, set this to sweep, then click apply. Now we will have a clear picture. Now go to frequency and set it to 2.4 gigahertz. Now you will be able to see the fields. So this field you can see these are traveling inside along this direction. Now change the field to 45 degree, the phase to 45 degree. Still you can see the field is going from down to up like this. Okay. Now change to 60 degree. You see the field has same direction. Check at the 90 degree phase, same direction. Now we see this has appeared as red. So this is the peak value. Now if we increase the phase, it will start decreasing like 120 degree. So it has faded. So 150, it is again faded. 180. So at 180, you see the direction has suddenly reversed, right? So when there is a sudden reversal of the direction, then it is a linear polarized antenna. And which fields we are considering? The fields that have the highest magnitude. These fields, there are some fields that are propagating in the horizontal direction also, but we are not considering them because their magnitude is very small. According to this color bar, you can see that these blue curves have very small magnitude. The red curve has almost 10 times the magnitude. Okay. So if you click on the 270, then also you will see that this is along this direction. So from this, what we can say, the antenna is polarized in y direction because this one is y direction. So antenna is in polarized in y direction here. Okay. And if for circular polarization, what we will be having with this variation, this electric, the tip of these electric fields will vary. Okay, so this red field you can select a one arrow that has the maximum magnitude and observe its effect. Okay, there is no need to consider all the arrows, but you should be selecting the arrow that has the maximum magnitude. Okay, then our field polarization is done. From axial ratio, you can also identify the polarization, but from electric field also you can find the polarization. Okay. And any more queries? So
participants, you are requested to ask if you have any query. Sir, very nice
If you have any
explanation.
query,
Thank
you
you,
can
sir.
ask. How can we add new material in HFSS? Okay, so in order to add a new material, what you can do, you can click here, right click, and there is a this button that is assign material, or you can double click here and go to material. When you click here, and this is a variation scroll bar, so click on the edit. Now these are the existing materials. Okay, if you want to create a new material, you can click on this add material. Then you can assign it a name and give the values, relative permittivity and permeability, all the characteristic of the material that are available to you. Okay, then you can also set the frequency dependency, and there are various models, piecewise linear model, Debye model. These are all associated with material engineering. They have very physical properties, and each model has a different mathematical equation that is relating the frequency dependence on the material and material characteristic. Okay, so from here you can add materials. Yes, you can add a new material that are not already available, but for the frequency variation, there are some limitations. Either you have the physical knowledge of the physical physics of that material, so that these are the few modes that are supported in HFSS. For frequency dependence, there are these. You have to check this. Okay. There are Debye model and multiple Debye model and Jordavic model. These are the frequency models. And if you have the frequency characteristic, then for each frequency point you have separate data. Then you can also use from there. Okay, so you can set them. I have not tried that, but this is possible here. But it is no, I don't know how many points they support. Okay. Okay. Are there any queries? For graphene, you need to find out its characteristic from existing literature. So if you have a frequency versus if you have frequency the data in tabular format for different frequency point, you have the characteristics of epsilon r and mu. Then you can use that. Okay, but we need to explore how many points it support by default, and there is an alternative way. What you can do, you can create multiple materials for different frequency ranges. Okay. Okay, so uh, that is all for today, and if you have any query, then please ask. Tomorrow I will try to start with the antenna array, and I will also cover one more antenna in the SIW tomorrow.
Sir, tomorrow will be a break. From a Monday, we will continue, sir.
Okay, okay,
So I think, sir,
okay. So
for today now there are no more queries.
okay, then
Thank you very much, sir.
thank you, Swati, and we will see you on Monday then. Okay. Bye everyone.
Bye, sir. Good evening, sir.
Good evening.
Dear participants, tomorrow will be a break. From Monday, we will start again at 9 o'clock. Session will start. So you are requested to join from Monday at 8:45 a.m. Thank you.